Okay, so as I alluded to in the last video, I believe, welcome to our video on free body diagrams when we have two objects. This is the first truly new thing you're seeing this year. All of kinematics, you kind of at least saw parts of that last year. In forces, basic forces and force on ramps, you also saw. This is free body diagram for two objects. We did not do anything really like this last year. We did do one experiment that involved this, but we didn't get that far into it. So let's read the description. We have a mass M1 resting on a frictionless table is attached to a string. The string passes over a frictionless pulley and is attached to a second mass M2 that is hanging in midair. A picture of the system is included below, right here. If the system is left alone, determine the acceleration of M2, the hanging mass, in terms of M1, M2, and G. So we're looking for the acceleration here. And what we're really looking for, well, I mean, if you want to predict what's going to happen here, there is nothing to hold M1 back. It's a frictionless table, so there's nothing resisting its motion. M2 is going to fall down, it'll pull on the string, and that'll pull M1 to the right. And notice, because it's connected to that string, if M2 moves down, M1 must move to the right. Likewise, if M1 moved to the left, M2 would go up. So these objects, even though they're not moving in the same direction, are thus connected. Okay? So because we have two objects here, what we're really dealing with here is what we would like to call a system, a collection of objects. And in this case, and in AP Physics in general, it's a good idea to get good at defining what a system is, or what system you're looking at. Our system would be M1, M2, the string between them, and this pulley that's also helping them to move. Okay? And those are the objects we're going to look at. It is actually important that the pulley is frictionless, and it's also important that, and it doesn't say this, but the pulley should be, essentially massless, and that string is lightweight and massless. Just some rules that we're going to follow before we get into the actual math. When you have two body systems like this, we're going to make the following assumptions. Our first assumption is that the tension in our massless string is the same everywhere. Okay? We're going to assume that the tension up here is equal to the tension down here, and that's the same everywhere. That's not exactly quite true, but it's pretty close to true, and it's a good first approximation. Later in the year, we'll see problems where the tension is not the same in two different parts of a string. We're going to assume that the string does not stretch or is not elastic. That's an important one. And because we're going to assume that, okay, so I already mentioned frictionless pulley and frictionless massless pulley. We're also going to, because the string does not stretch, we're going to make the assumption that the acceleration of one object equals the acceleration of the other object. In other words, the acceleration of M1 equals the acceleration of M2. It might be in different directions, but the magnitudes of the acceleration are the same. And that's the case because that string does not stretch. If you were to move M2 down 1 meter, that means M1 must move over to the right 1 meter. Therefore, it's also the same idea that because the string does not stretch or compress or anything, that the object would move at the same rate. They would have the same speed the whole time, and therefore they would also have the same acceleration. Okay, so those are our basic main assumptions, that the tension is the same throughout the string, and that both objects accelerate at the same rates. Now that we've got that out of the way, because we have two objects, we actually have to do two different free body diagrams. So here's what I'm going to do. I'm going to draw a free body diagram up here for, or I'll just draw it right here, for M1. I'm going to start with that one. I'm going to put a dot. I'm going to label it as M1. It's very important that you label each free body diagram this time. Before, some people would leave off labels on free body diagrams. Now you can't, because we have two different objects, two or more different objects. We need an axis. We're going to make our axis the standard axis. Y is up, X is to the right. And so we know that for M1, there is a force of gravity acting down on M1. So that's going to go down here. We're going to label it FG, and I'm going to put a 1 next to it. to symbolize that we're dealing with, this is M1, this is the first object, okay? It's important because there's going to be another force of gravity for this one, and that's going to be Fg2. Because it's resting on a surface, a flat surface, horizontal surface, we're going to draw a normal force, and we can just write Fn here because there's not two different normal forces. M2 is not resting on the surface. And our last force that we're going to draw in is the force of tension. And again, since the tension is the same everywhere in the string, we don't have to write T1 or T2. Okay? That's pretty much it. There's no friction, so there's nothing opposing the motion. That's it for that free body diagram. We're also going to make a free body diagram for M2. And here is where this gets a little tricky. The first part, that was pretty much okay. You remember on ramps, I asked you that one of the things we're going to do differently on ramps is we're going to tilt our axes to align with the direction of motion. We're going to do something similar here. We just got done saying that if M1 moves to the right, M2 must move down. Well, rightwards for M1 would be in the positive x direction. And you're going to have to trust me on this, but it makes the problem so much easier if M1 moves to the right, and that's the positive x direction, then whatever direction M2 moves in should also be the positive x direction. In this case, if M1 moves to the right, M2 would move down. So for my axis for M2, I'm actually going to draw it like this, with the positive x direction being down and the positive y direction being to the right. Now, why do I have to draw the positive x or y direction to the right? Because I need to keep the same orientation between our x and y directions. Y is 90 degrees counterclockwise from x in both cases. So again, why I'm tilting the, or rotating the axis this far is because if M1 moves to the right, then M2 moves down. To the right for M1 is the positive x direction, and it's going to make your problem much, much easier if you also make for M2 the positive x direction to be in its direction of motion, in this case down. It is possible to do it with a standard axis, but then you're going to be comparing accelerations. You're going to have to remember which direction the acceleration is in. Doing it like this, we don't have to deal with that. Doing it like this, we simply see that the x direction is in a certain direction, and we can say that it's like in the direction of motion. That's how I usually refer to it. Okay, so it's going to take a little bit getting used to. Make sure that you understand why we're doing this, and if you don't understand, please come ask me questions. As far as the forces on M2, we have gravity pulling it down. That would be Fg2, and we have tension pointing upward. That would be T. Okay, and again, remember that T is the same here and here. Now, now that we have the free body diagrams drawn, we need net force equations in each direction for each object. So, since there's two objects, two directions, it's a total of 4 net force equations. For object number 1, let's do the y direction first. F net y equals, in the positive y direction, Fn minus Fg1 equals m1 ay. It's important that I put that m1, because otherwise I don't know what mass you're talking about. Are you talking about m1 or m2? Now, m1 does not seem like there's any reason for it to start accelerating upward or accelerating down onto its table. It's not going to accelerate in either of those directions. So the acceleration in the y direction must be 0. So I'm going to cross that off and write 0. And I'm going to conclude that Fn equals m1g. The force of gravity on object 1 is equal to the object 1's mass multiplied by the acceleration due to gravity. F net x is very simple. In the positive x direction, there's tension. There's nothing in the negative x direction, so tension must be equal to m1 ax. And we don't know what ax is. That's what we're trying to solve for, so I can't do anything there. For object 2, we have the following. In the y direction, there's nothing. There are no forces in the y direction, so F net y is 0 newtons. F net x, be very careful. The positive x direction is downward. Again, we set the positive x direction as downward because if M2 moves down, that means M1 must have moved to the right. And since the positive direction in the x direction for M1 is to the right, we're going to go with that for M2 as well. M1 moving to the right means M2 moves down. Both of those are our positive x directions for those particular objects. So Fg2 is actually the positive force because it's in the positive x direction, minus the tension equals M2 AX. Now we're trying to find the acceleration in terms of M1, M2, and G. That's it. So we have those terms, we just don't have them written the way we need them to be, because there's also a t in there. We need to figure out how to get rid of that t. Thankfully, because I have a bunch of different equations, I see that t is equal to m1ax, and I have a t in this equation. If I substitute this over here, I can get rid of that t. So rewriting, I have, instead of fg2, I'm going to write m2g minus m1ax equals m2ax. I'm going to add the m1ax over to the other side. So I get m2g equals, and since I will have an ax in both those terms, I'm going to take the ax out, leaving me with m1 plus m2. And ax outside the parentheses. If I redistributed this ax to both sides, I would have m1ax plus m2ax, which is what I would have gotten if I just added this over. I just skipped a little, or not skipped a step, I kind of did two steps at once. To get ax by itself, I divide both sides by m1 plus m2, and I find that ax equals m2g over m1 plus m2, and that is the acceleration for this system. Okay. Notice that it's the acceleration of both objects, not just one or the other. It's the acceleration of both, since they have the same acceleration. Also, let's do some looking at this result. M2g, what is that really? What is M2g? Well, quite obviously, it's the force of gravity on M2. And if you think about it, that is the force that's driving this system to move in the first place. The only thing making M1 move here is tension, but tension is also acting on M2, and it's the same tension. The tension, therefore, is what we call an internal force. It doesn't come from outside the system. Remember, our system was M1, M2, the string between them, and the pulley. The tension comes from something inside our system. We're accounting for the string in our system, therefore the tension must be an internal force. And when we talk about net forces, we always talk about a net external force, something coming from outside our system. So tension is an internal force here, so it doesn't affect the net force on the system. Now you could make the argument, well, tension obviously is the force that moves M1 forward, so it definitely affects the acceleration of M1. That's true. But we weren't just looking at M1. We were looking at the entire system that is in motion here. Okay? And that tension it's not a driving force for the system. The tension is completely internally contained. So M2g, the force of gravity on M2, is the force that drives this whole system. You could say it's the net force on the system. There's no other force that's causing acceleration. Like I said, tension is internal, and Fn and Fg1 are balanced. There is no acceleration for that object in the y direction. Fg2 is the only force that is outside the system. It results in it comes from the interaction between M2 and the Earth is outside of our system. So the net external force is just the force of gravity on M2. M1 plus M2, quite obviously, is the total mass. So very interestingly, look what we have here. We have the force of gravity on M2, which is really the net external force here in this situation, divided by the total mass. Net force divided by mass equals acceleration. This is very simply a restatement of Newton's second law, which is really, really cool. The last thing I want to show you is some limiting behavior. If you're in calculus, great. If you're not a big deal. We want to look at this equation and see if we can use it to predict what should happen if M1 becomes very, very, very large, if it gets close to infinity. Okay? So if you don't look at the equation, you just look here. If this gets really large, that's going to be really hard for M2 to pull it down and accelerate it to the right, correct? So you'd imagine that there's not a lot of acceleration. we look at our equation, that seems pretty reasonable. If M1 gets really big, it's almost like M2 doesn't even exist. It's almost like M2 is negligible compared to M1. And if M1 gets really big in this denominator, then M2G isn't going to grow, the denominator keeps growing, your limit tends towards 0. In other words, the bigger M1 gets, the smaller the acceleration gets. Which is just what we said. That seems like it makes sense. Okay? We look at limiting behaviors because we want to see if our ideas make sense. Let's look at another limit. What if M2 instead gets a lot bigger? This one's a little trickier because we have two places where M2 is in the equation. You might say, oh, well, if M2 gets bigger, then it's going to accelerate faster and faster downwards at a greater and greater rate, and the more you increase M2, the more you increase, excuse me, the more you increase the acceleration of the entire system, and it'll go to infinity. But if you add mass to M2, not only are you increasing the force downward, you're also increasing the mass of the system. And we know that increasing mass leads to increasing inertia, which means it's harder to cause something to accelerate. So let's look at this. If you increase M2, the top's going to get really big, and the bottom's going to get really big. The bottom, M1 is going to become almost negligible. So you end up with M2, you end up with something that approaches M2G over M2. Cancel out those M2s, and you're left with a limit of G. Interestingly, there's a limit to how big the acceleration can get. If M2 gets really, really big, then M1's function is to kind of hold back the acceleration of M2 a little bit. If M2 gets really big, and this is much smaller compared to it, it's not going to do a very good job holding it back. But it's not going to cause infinite acceleration, because we know that if there's not really anything holding M2 back, it's almost like it's in free fall. And in free fall, the acceleration due to gravity is G. And that seems to make sense. It wouldn't accelerate at an infinite rate. It would be as if M2 is almost in free fall, and therefore that would be have an acceleration very close to G. So these limiting cases, the reason we look at them is to make sure that the equation that we're using here, this one, under some common limits would make sense and makes physical sense. In this case it does, so we think that this should be pretty accurate. This must be how this actually is going to work. Okay? That's a simple free body diagram two-object problem. There's a lot of variations to this. We'll study a slightly more complex one in the next video. But I would make sure that you're comfortable with this. You're going to see in this unit a lot of two-body systems. So it's good to get comfortable with the ideas now. Probably the toughest one is to understand why we're switching our axis like this, to make sure we're writing the net force equations correctly, and then making sure that we're substituting our equations correctly as well. I'll be back for one more example of this in the next video.